Hello, Dr. Chan, can you hear me?
Yep, I can hear you.
Is it okay if I ask some questions?
Sure.
Well, it's only really one question. Are we expecting assignment 8 tomorrow?
Yes.
Okay, sounds good.
All right. It's 7 o'clock. Let's go and get started. All right. Good evening, everyone. How's everyone doing today? Everyone's doing good. All right. So we are in the last 2 weeks of the semester. So, we're quickly, very quickly winding down. And so this topic on buckling and stress stiffening, this is going to be our last kind of topic that we'll go over together. And so just like I said last week, we're going to go over kind of a little bit of the background information for the activity today. And then Wednesday we'll perform the activity. And then next week is our last week. And so, just to kind of remind you, everyone, the plan for next week is that I don't have anything planned for next week, although, I can certainly teach on something if you guys want me to. But for next week, what I'm reserving it for is kind of just project workshop. And so, what the hope is for next week is that you guys have kind of started on your final projects and you have questions about the final project. You want me to look at something or you're getting some errors. And then next week we can kind of work together and kind of work through those. And so next week will basically be dedicated office hours for just for this class for Monday and Wednesday. Okay.
Dr. Chan.
Yes.
Having said that, do we have to email you if we're gonna go, or if we?
Oh no, just
stop by.
Just show up if you need help. But I don't at this point I don't plan on teaching anything. And so if you don't need help on your project, or if you feel like you're doing okay, then feel free to kind of skip out on lecture next week too, because yeah, it's mostly just individual help for next week. So next week is only if you need help on your project. Yeah.
Sounds good.
Okay. All right. Yeah. So this week is the last topic. This week is the last activity. So yeah, we're quickly getting to the end of the semester. Okay. All right, let me see. I think that's about it. There's not really much else to announce. Are there any questions I can answer about anything before we get started for today? Okay. All right, so let's go ahead and get started. Today's lecture should be pretty short, so hopefully we'll end early. Just because the amount of content is not that big. Okay? But the topic for today and the topic for our activity Wednesday is this idea of buckling and stress stiffening. All right. So this, I kind of saved this topic for last for a couple of reasons. And so, the main reason I kind of saved it for last is because it's pretty simple. There's really not much to it in terms of answers. So it should be a fairly short activity. Today's a fairly short lecture as well. And so I think it's kind of good to end on something like this, especially as everyone's starting to work on their final project. But I think it's also a little poetic in a sense too, because it kind of brings us back a little bit to kind of where we started in this semester as well. Okay. And so let me kind of bring us back then. And so, one of the objectives that is commonly used for FEA that we use, for a lot of our activities is we want to determine if a structure is going to fail under its given load. So, we have our structures, we apply our boundary conditions, we apply our loads and constraints, and we want to check and see if it fails. Okay. The primary way that we did this was that we ran FEA and we checked the equivalent stress field within the structure. And what we said was that if the equivalent stress was greater than the yield strength, or greater than or equal to, I guess, is greater than or equal to the yield strength of the material, then the structure would fail. Okay. And of course, we had things like factor of safeties, of course, that would modulate that as well. But generally, that was our approach. And so, we took our CAD models, we applied our boundary conditions, we checked the equivalent stress, and we checked to see if it was greater than the yield strength. Okay. Okay. That's one way for a structure to fail, right? So I would say that's the most common way, or the way that people generally think about. But there are other ways that structures can fail as well. Okay, so this criteria right here, this is often reliable when the structures are failing under tensile load. So when the structure be basically being pulled apart. So something a little bit different happens when a structure is subjected to compressive stresses. So stresses that kind of push the structure kind of towards itself. And so for compressive loads or compressive stresses, we have to worry about, or we have to think about buckling as well. Okay. So what is buckling? Right? And so I think the easiest way to kind of show buckling is through kind of a visual example. Okay. And so let's go over an example that I think, hope that, probably many people have experienced kind of firsthand, which is crushing a can of soda or a can of ginger ale or just whatever you drink from a can. Okay? So let's say that we have a can. And of your favorite soda, unspecified because I'm unsponsored by any soda companies, at least not that I'm aware of. Okay. And let's say that you put this can of soda on the ground and you step on it with your foot. Okay. And so what that's going to do is that it's going to apply a compressive load. And so we're going to apply loads that kind of squish the can like this. Okay. And what you should notice, and kind of what you can probably imagine in your head, is that this soda can is going to kind of crunch together, right? And so it's going to end up something like this. So it's going to be much shorter than it was before. Okay. It still has kind of its ring shape. Okay. But the structure is kind of compressed like this. And so the sides of the soda can have kind of almost like crumpled, like a piece of paper. Okay. So what's happening here is actually interesting. So on the one hand, you can say, or one hand, you can kind of postulate that, by applying this compressive stress, or by applying this compressive load, we've increased the amount of equivalent stress in the can beyond its yield strength. And so what we're observing is yielding. Okay. That is possible, and that could be the case for some cases. Okay? But another thing that's happening here is something called the stress stiffening. Right? And so the stress stiffening effect kind of gives a reason why we see that kind of jaggedy look, that kind of crumpled look that you associate with kind of crushing a soda can, or even crushing a water bottle as well. Okay. So the name for this effect is kind of interesting. And so, normally this effect is kind of brought up in different contexts. That's why it's called the stress stiffening effect. But we're actually going to be looking at the opposite. So you can almost think of it as like the stress weakening effect. Because what happens is that when you apply a compressive stress to a structure, apply a compressive stress to a structure, basically a stress that's going to push the particles of the structure kind of closer together. What happens is that the bending stress or the bending strength of the material will go down. And so, of course, the operative word here is bending strength. And so bending strength is basically the ability for your structure to resist bending moments and bending failure. Okay. So it's very specific. And so if you kind of look at the structure of this crumpled soda can, you can see that I kind of drew it in a very specific way with lots of bends, right? So all these jagged points are basically lots of kind of bending failure. That's why you kind of have that. That's why you kind of have that pattern. Okay. On the flip side, the opposite the opposite of this effect, which is why the effect is called stress stiffening, is that if you apply a tensile strength, you actually, or tensile stress, you actually increase the bending strength. Right, and so that's actually interesting. And so if you actually took the soda can and actually pulled it apart lightly, and so there's a couple things that you're kind of dealing with there. So if you pull this, of course, if you pull the soda can away too much, then you're just going to have just regular tensile failure, and you'll kind of rip the can apart. Okay, but if you kind of pull on the can with just enough tension, and you actually try to bend it, right, it's actually going to be harder to bend than if you didn't apply that tensile strength at all, tensile stress at all. A very kind of interesting effect. But we're not worried about tensile stresses here. When we're talking about buckling, we're talking purely compressive stresses. Okay. All right. Any questions on this so far? Okay. So that's stress stiffening. So what is buckling? Okay. So buckling is kind of a special case of stress stiffening. So when a structure buckles, what we mean by that is that there is enough compressive stress applied to our structure such that the bending stress approaches zero, or is basically almost zero. All right, so that's what we mean by buckling. Okay, so buckling is kind of, you push this compressive strength or compressive stress all the way to a certain point where the bending strength is basically zero. Okay. All right, sorry. Oh yeah, sure. Dude, sorry, you scared the shit out of me. Okay. Right. So buckling is you basically compress the structure enough such that the bending strength approaches. Okay. And so that's kind of a very special point, because once the bending strength basically approaches zero, then just any kind of slight perturbation will basically cause a structure just completely collapse on itself. Right? And so in theory, if you have a soda can and you're applying a compressive force to it, right? In theory, if you were to apply it perfectly in such a way that it perfectly compresses the soda can, you can keep applying that compressive stress and buckling wouldn't occur. Okay. And what I mean by that is that the structure actually wouldn't collapse. Because the interesting thing for most engineering materials, if you look at just purely the compressive strength of the material, usually it's going to be a lot higher than the tensile strength. And so I kind of want to make this clear. So when you observe buckling, you know, it's not exactly compressive failure. That's not really the right term. Okay? And so buckling is it's not the effect that, you know, we're you know, it's not the same as like kind of pushing our structures so close together that we're exceeding this compressive strength. Right? What buckling actually is that, you know, by applying that compressive stress, you're weakening the bending strength of the material. And so buckling is actually failure in bending. It's not failure in compression. Okay? So it's kind of a nuanced point and kind of a you know, something you might say is kind of pedantic, because, you know, technically speaking, you know, we can still say it's compressive failure because it's failing when we're applying compressive stress, but it's not failing because, you know, we're reaching that compressive strength. It's failing because of buckling. So it's, you know, if you're a contractor, if you're someone that's building a structure, you know, you'd probably say, who cares? You know, it's failing either way. You know, it doesn't matter if it's failing in buckling or compressive failure or whatever. But, you know, for us, you know, for those of us on kind of the analysis and on kind of the design side, that's something that's important, because there's ways to kind of design your structure to be strong against buckling, but, you know, may leave you a little bit more vulnerable to compressive failure. Okay. Any questions on this so far? Sorry about that. It was just yeah, it was just the lights are off, and so, you know, you're totally fine. You're totally welcome. Just start on the little bit. Oh no worries, no worries. Yeah. All right, so let's see how, let's kind of see this this occur through kind of another kind of a more controlled example. Okay. And so let's look at the this is kind of a demonstration of buckling. You can do this in ANSYS too. We're not going to do this in ANSYS, but, you know, you can do this kind of thought experiment, and you can kind of see the stress stiffening effect in action. Okay. Okay. All right. So for this experiment, you can have a typical beam here. Let's go ahead and fix the beam on one side, and then on the other side, we'll apply a roller constraint. Okay. And so we'll let the beam kind of translate freely in the X direction on the right. Okay. On top of the beam, we're going to apply a distributed load. So this distributed load we'll call P. Direction. We'll apply a force F. Okay. So what the force F is going to do, or the role of the force F, is that this force F is going to let us apply basically a tensile or compressive stress on the beam. And so basically the experiment that we're going to do is we're going to modify this force F, and then we're going to see how that affects the bending strength. Okay. Right. On the other hand, this node P, okay, I've applied it in kind of a very specific way. So this P, you can see, is being applied perpendicular to the beam. And so what this P is going to do is that it's going to apply a bending stress to this beam. And so in this experiment, we're gonna have P, we're gonna keep it constant. And so we're going to apply basically the same amount of bending strength or bending stress to the beam. Okay. But what we're going to vary is we're going to change the value of F across various values. So as we change the value of F, so we're going to start it as from a tensile load, and then we're going to put it, and then we're going to make it negative, and we're going to make it compressive. Okay. So as we change the value of F, what we're going to do is we're going to observe the maximum deformation in the beam. So there's a couple of things that you should know about this kind of experiment. Okay. And so on the first case is kind of what we expect in terms of the trend. Okay. And so as F goes from tensile to compressive, what we should observe is that the deformation should go up because the bending strength is going down due to the stress stiffening effect. Okay. So that's the first thing that you'll notice. Okay. The idea is that the lower the strength, the higher the deformation is going to be. Another note that I want to make is that this deformation here is going to be perpendicular to the beam. Okay, so basically what you should see is that the beam is going to increase its amount of bending. Right. And so in other words, what we're going to observe. And so I'm going to exaggerate here. It's not going to be this much, is that it's going to look like this. Right. So we're going to start with something that maybe is a little bit deformed, and then it's going to go kind of more like this, and then more kind of like that. Okay. So we're going to go in this direction. So here we have the tensile mode. Here we have compressed. So I wanted to mention that because that's a little bit hard to see, or that's a little bit hard to kind of envision from the figure that I'm about to draw. But just remember that this is bending. We're talking purely about bending strength when we're talking about stress stiffening. Okay. And so the graph for this looks like the following. So we're going to have a graph, looks like this. Okay. Let me go ahead and draw the middle point here. So on the horizontal axis, we're going to have the value of F. And then on the vertical axis, we're going to have the amount of deformation. And so this dotted line right here is going to be a value of 0F. Okay. And so to the left of this dotted line are going to be compressive forces of increasing magnitude as we get closer and closer to the vertical axis. And on the right of the dotted line is going to be tensile forces, okay, with increasing magnitude as we get further and further away from the dotted line. Okay. All right. And so if you do this, and so you can do this in ANSYS, and so you can make a very simple CAD model for a beam, apply these loads, and then observe how the deformation changes as you increase, or I guess decrease in this case, the value of F. Okay. And so what you should see is a graph that kind of looks like the following. So I'm going to have a slow upward trend. Right. So this is generally what we expect. And so, as we make the compressive stresses within the beam higher and higher, then that decreases the bending strength. And so the amount of bending deformation is going to go up and up. Okay. All right. Any questions on this so far? All right. And so if we continue this graph to the left, and so you can see from this graph here, we have a fairly steady increase. And so going from right to left, the increase is getting slow, okay, or it's fairly steady. But if we keep continuing this to the left, and so we keep, making the F more and more and more compressive, eventually we're going to reach a point where the graph is going to kind of shoot up. So at this point, this is when buckling is occurring, because when the bending strength is basically 0, that means we're going to have basically infinite deformation, or in other words, our beam is going to fail. So eventually, we'll reach a point that looks like this. So steady, 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 and all of a sudden it's going to kind of shoot up like that. Okay. And so this value here, kind of where it starts to shoot up, this is the point of buckling. So this point is really important. And so this is often what we are interested in from an ANSYS perspective, is where's the point of buckling. Okay? But we want to know, basically, for the loads that we've applied onto our structure, are they, first of all, are they going to cause buckling by themselves? Okay? Usually not. So usually, for a default configuration, as long as your structure is kind of in a fairly reasonable state, you're not going to cause buckling in kind of a default state. Okay. But but from then what we can see is, if we were to increase the amount of loads, what's the point of increase where we actually are going to see buckling? Okay? In other words, how much? So basically, when we do buckling analysis in ANSYS, we're basically doing the exact same thing as this experiment, right? And so in this experiment, in this kind of very simple experiment, all we did was we kept increasing the compressive load until we reached this point of buckling, okay? For a real structure with kind of real boundary conditions, this is not as easy to do because our loads are kind of in a much more complex state, okay? And so in these situations, we rely on ANSYS to kind of help us give us that answer. Okay. And so the tool that we're going to use in ANSYS is called eigenvalue buckling. And so, for the rest of the class today, we're going to discuss, how to set this up in ANSYS and what you can kind of expect from the results and kind of how do you interpret the results.
Dr. Chan,
Yes.
I might have missed this, but is the Euler's buckling equation used at any point in ANSYS?
I think for simple beams it is, and so we'll go over that in the end. But for more complex structures with more complex geometries, I think it has a different way of computing that.
Yeah. I see. And that's eigenvalue buckling?
Correct. Yeah. But actually, the activity that we're going to be doing on Wednesday, it is essentially a structure of beams. In fact, I think the geometry has already been converted to beams for you. And so in theory, you could apply Euler's theory to predict buckling as well. Yeah, because it's essentially a beam. I mean, it's a complex, kind of triangular structure, but in theory you can use Euler's beam theory for that. So I think ANSYS does kind of an approximation of that to an extent for those, but for kind of three-dimensional structures or even two-dimensional structures, I think it does something a little bit different.
Sounds good.
Okay. All right, so eigenvalue buckling, and so this is the tool that we're going to use, and it's used a lot in ANSYS because it's relative to a lot of other things we've done in this class. It's relatively simple and relatively fast to do. Okay. One note that I want to make, though, is that this eigenvalue buckling is what we call a linear buckling analysis. Okay. With the emphasis there being on linear. So this is important because, technically speaking, when you're talking about buckling and you're talking about stress stiffening, these are all nonlinear effects. And so that experiment that we talked about earlier with the beam, technically that was done with nonlinear effects turned on. So that was with large deformations turned on. Right. And so if that's the case, so if buckling and stress stiffening is nonlinear, then what does it mean to do a linear buckling analysis? That kind of seems like a contradiction. And so a linear buckling analysis, it is reliable, and so it is a real thing. But all that really means is that all of these kind of buckling and stress stiffening effects, we're basically doing a linear approximation of these effects. Okay? So this is actually a problem because in approximating the buckling effects, what it tends to do is that it tends to overestimate the amount of loads that are needed to cause buckling. So that's bad. And so in a world of conservative design, when you want to make sure that your structure is going to be sound, you don't want to overestimate, at least in your analysis, you don't want to overestimate the amount of loads that are needed for buckling. Okay. Because if you have a situation where you're designing a structure and you're saying that, oh, this according to my analysis, the structure can withstand, let's say 10,000 pounds in buckling. Okay. But if that's an overestimation, but in reality, you put the structure in practice and it buckles at say like 8,000 pounds, now you're in trouble because if the safety was relatively low and you expose the structure to 8,000 pounds, then your structure is going to fall apart and you're probably going to lose your job. Okay. So, I'm bringing this up because it's important because, when you're using eigenvalue buckling, you want to make sure that you have an adequate factor of safety on your results. Okay. Right, because in kind of a situation where you're overestimating the loads and that you're overestimating the loads, you want to make sure that there's an adequate factor of safety so that you kind of account for that overestimation plus kind of your usual kind of factor of safety. And so what I usually tell people is that if you're designing something with a certain factor of safety or a lot of other aspects of the design, if you're going to be using linear buckling analysis, bump up that factor of safety a little, even just a little bit will help a lot, just to make sure that your results are still reliable. Okay, so that's kind of a really important caveat. So eigenvalue buckling, it's really fast, it's really convenient. You can do it in once you kind of understand the process, you can literally do it in 5 minutes. But you want to make sure you take the results with kind of a grain of salt, or not a grain of salt, but you take the results and you kind of make sure that you apply an appropriate factor of safety to make sure that your results are reliable. Okay. All right. So how do we actually initiate this? How do we actually perform eigenvalue buckling? Okay. And so just like modal analysis, our first step is going to be a static structural simulation. What we're going to do is we're going to link the eigenvalue buckling analysis to the static structure. All right, so this is important because the way eigenvalue buckling shows your results, it's going to be confusing at first, but the way it displays your results is that it displays it as what's called a load multiplier. Okay? And so what that means is that it's gonna read all the loads that you applied in static structural. And then what it's going to tell you is that if you were to multiply those loads by this particular factor, that's how much you would have to increase the loads to cause buckling to occur. Okay. So let me kind of show you just a very quick example. Okay. So let's say we have a triangular structure. And so let's say that we have a structure that looks like this. So let's say that we have a couple loads being applied. So we have a load of 500 newtons here, and a load of 300 newtons. Okay. Great. So if you were to run this through eigenvalue buckling, okay, maybe what it will tell you is that it will tell you that in order to cause buckling, your load multiplier is going to be, maybe 2.5. Okay. And so what that means is that if you were to increase all the loads in this configuration by a factor of 2.5, then that would cause buckling. Okay. In other words, if I were to draw kind of the same geometry here, and if I were to increase these loads by a factor of 2.5, okay. So 500 times 2.5, that's what? That's 1250 newtons, okay. 300 times 2.5, that's what? 750 newtons. Okay. This would buckle. And so one thing you should notice here is that, this load multiplier, it doesn't apply to each individual load, right? That load multiplier is going to apply to the all the loads together. And so kind of keep that in mind, when you're doing this. Okay. Because what ANSYS kind of implicitly assumes is that when you apply these loads in static structural, and you want to increase these loads, ANSYS is basically assuming that you keep these loads in kind of the same ratio. Okay, that's why it applies the load multiplier to all of it. If you're interested in kind of individual loads in terms of what will cause buckling, you can do kind of a more complex kind of buckling analysis where you can kind of take each load individually. A lot of times that's kind of what you're interested in, especially if you know that kind of one particular load is going to cause buckling more so than the others. But eigenvalue buckling is kind of a almost kind of like a quick and dirty way to kind of see buckling. Because of its linear nature and because of its it applies the multiplier in broad strokes. It's probably not going to be the one that you publish your scientific report about, but it kind of gives you a good sense of how structurally sound or how resistant to buckling it is. Okay? Because if you have a buckling multiplier of like 20x, then in that case I would say that you probably don't have to go through a more sophisticated analysis. You're probably not really in danger of buckling, with a 20x multiplier. But, if you go through eigenvalue buckling and you get a multiplier of like, even like 2, I would say that, I would kind of re-examine your structure and maybe do a more complex buckling analysis to kind of see where the points of weakness are and where you kind of beef that up with design. Okay. All right. Any questions on this? All right, so kind of a couple practical notes kind of before we end the lecture today. Okay? Most of the time when you're interested in buckling or you're performing buckling analysis, most of the time it's going to be on structures that are comprised of a lot of slender beams. Okay? Okay. And so, kind of like what Ivan mentioned earlier, for beams, for slender beams, there is an analytic formula for predicting buckling loads. That formula is the following. So F, the amount of force that's been caused buckling in a slender beam is given by pi squared times the Young's modulus times the moment of inertia divided by the length. Okay, so E here is the Young's modulus. I here is the moment of inertia of the cross section. L here is the length. And so, having a formula like this is always useful. We talked about, a couple of weeks ago, we talked about verification and validation, right? Whenever you do any kind of finite elements or any kind of computational work, it's always a good idea to kind of check your work, especially with equations like this. Okay? So if you have an equation like this that's available and you can kind of just quickly do it just to kind of check your results, make sure they're in the same ballpark, that's always kind of good to do. Okay. Another thing you can do with eigenvalue buckling that is kind of more cool than is useful is you can view the buckling modes. And so buckling, it's kind of similar to how modal analysis is. So, not only do we have kind of one buckling load, but we also have multiple modes that are available. Okay? And each buckling mode kind of has its own unique way of buckling. Okay? But even more so than the resonant modes, most of the time you're not going to see the higher order buckling modes, just because if you already kind of push past that point of the first buckling, then your structure is going to fail anyway. So this is kind of more just for fun and for more kind of for the mathy people that kind of like to view these things. But you can view them, but just remember that when you view these modes, these are purely just for visualization purposes. So each mode basically is associated with a different load multiplier. Okay? But again, you're not going to, most of the time, you're not going to reach the higher load multipliers because you're going to fail kind of way before that. For example, let's say that we have mode 1, a simple beam, maybe it fails, like maybe it buckles like this. Maybe mode 2, maybe the bending kind of occurs kind of further down the beam. Okay. Again, the different modes, it's not particularly useful because you're almost never gonna see the higher order modes unless you really try to plan an experiment for it. You're gonna fail way before that anyway, but it's kind of neat. It's kind of neat to see it. Okay. Any questions on any of this? Okay, all right, so that's all I got for today. And so, buckling, fairly straightforward. And I think what you'll see from the activity Wednesday is also fairly quick and fairly straightforward too. So, it's our last activity. I know work for the final project is ramping up. So, this last activity is going to be, relatively chill. Okay. All right, so thank you guys for coming today. I hope you guys enjoy the rest of your evening, and I will see you Wednesday for our activity.
Thank you, Dr. Chan. Have a good night.
Bye, everyone. Have a good night. All right, any Zoom people, any final questions before I close up the call? Mariah, Marilyn, Trevor, anything?
No, I'm good, Dr. Tran. Thanks.
Okay.
Have a good night.
Thanks. Have a good night. Good night, everybody. Mariah, I'll see you tomorrow for your defense. I'll probably join virtually, so because I need to be home tomorrow, but I will see you. I'll see you.